Okay, I think we're going to get moving here. There are probably a few people that will still be wandering in a little bit late. By way of introduction, my name is Brendan Burrish. I'm a distinguished engineer. I live in the United States. I've been part of Cisco for 29 years, and I present at Cisco Live in the US, in Europe, and then in Australia. Couple things here that I do want to cover quickly. Hopefully this will be the last time you see this, but we do have rooms that track all of the scheduled sessions. There is one for this, of course. I did post the slide deck in there this morning. In the event you can't get it through the app, it's also available up there, so you're welcome to download slides up there. The other thing I will tell you during the course of the presentation, please feel free to ask questions. I'm happy to stop and take them. I have a mic, or I will do my best to repeat them. We're at the last day, last session. I think everybody's weary for a variety of reasons, so I'll do my best to get us out on time, maybe even sneak out a bit early. And I notice we've got a variety of people, myself included, with luggage sitting here, so we probably have people wanting to get dashed off to the airport. So we'll do our best to keep everything on track. Hopefully everybody had a chance to read through the abstract, but if not, this is essentially the order of events that we're going to be going through the course of the presentation today. And I generally divide this into two halves. We're going to spend the first half primarily talking about how we go about building a modern on-premise architecture for data center. So we'll talk about VXLAN a bit and how we construct a fabric. More importantly, we'll talk about how we enable multi-site capabilities, because that's really going to be foundationally the pivot point for then the second half, where we talk about all of the connectivity out to the public cloud, how we naturally extend networking to the public cloud, and then fold security in, and then we'll draw to a close. So that's kind of the order of events here. So let's get going here. So I've actually used this slide a couple times this week. I think it's important to recognize that data center networks are in the midst of a transition, and you could argue that's been going on for a long period of time. We've really seen customers move, or in the midst of evaluating, moving from classic three-tier architecture to now the VXLAN or overlay-based models, which started out as a bridging, kind of very archaic sort of technology, but now has really modernized and matured to supporting a very scalable, routed architecture. And the reason we've done this, or the reason that customers are looking at this, is primarily for some of the challenges that have arisen around three-tier architecture. And so while three-tier architecture was very proven and very widely deployed, it came with some set of challenges, many of which you're probably familiar with. We typically ran spanning tree, and spanning tree resulted in unutilized links, suboptimal forwarding. We also had limited scalability. And so there was a variety of things that were not conducive to what was going on in the data center, particularly given the changing traffic patterns. And if you look at the traffic patterns in the data center right now, we know that a decade ago, traffic typically came in from the north side, i.e. towards the internet, and moved down into the data center and then returned out. Now we know that the traffic patterns, by way of a percentage, are 8 times as more likely to move east to west. Meaning for every session coming into the data center, I have server-to-server sort of traffic that's going to be 8 times as much. And this has really given rise for the need for an overlay-based system in terms of how we construct the network. And this is where VXLAN comes into play and is the growingly important technology that is the prevalent way that we deal with this. So let's look at why VXLAN is really the preferred choice. And when we say VXLAN, we mean VXLAN EVPN specifically. And we talked about some of the challenges on the left side with that classic three-tier model. And so really what we look at VXLAN EVPN for is, how do I enable any workload anywhere? And that's inclusive of the cloud. I think that's why everybody's here for this particular session. So seamless VM mobility is a huge part of this. We also look at a more efficient sort of network that leverages a layer 3 based routed underlay, provides ECMP, and we also then leverage VXLAN for data center interconnect. And when we talk about data center interconnect, that's site to site, and also for the purpose of today's discussion, and more importantly, that's going to be site to cloud based connectivity. Now, many of you probably through the course of the week have gone to sessions where they covered Nexus Dashboard, and broadly speaking, Nexus Dashboard Fabric Controller. We're not going to spend a lot of time with that platform today, but it is worth understanding and reminding everybody that This is our primary automation, management, and visibility system for VXLAN EVPN networks. Some of you know we also build ACI, and that's going to be folded into a broader set of common tooling for both methodologies, both ACI and NDFC, and when 4.0 gets here, we'll run under the common Nexus dashboard. So this is how we manage the network, orchestrate the network, and facilitate all the ongoing operational care and feeding of the network on a day-to-day basis. Now, let's go through some of the building blocks. And we're going to kind of systematically build this like a cake. And I guess, I probably should have put security on top, because if we're building from the bottom up, you could argue that the security discussion will be last. But we're going to build it from the leaf to the spine to the border gateway, and we'll talk about how we fold in security. We're going to talk about what the roles and responsibilities for each of these devices will be. And again, that's going to lay a lot of the foundational concepts for how we enable cloud connectivity and cloud-based security in the second half of the session. Now, the other thing that VXLAN EVPN is very pivotal for, and some of the aspects of it that are very, very appealing, are what you see listed on the right-hand side of this illustration. So if you know how standard-based Ethernet worked, we know we had a 4K VLAN encapsulate, or namespace rather. And VXLAN expands that to 16 million. So we have a significantly larger namespace to work with. We also now support seamless VM mobility. We talked about that. We're going to talk a fair bit about the notion of a routed layer 3 underlay, which leverages equal cost multipath, cross-sectional bandwidth, all fully utilized, richer performance, better scale, better resiliency across the entire fabric. And we'll talk about the fact that VXLAN, because it is a multi-tenant architecture by nature, is very, very conducive to segmentation and, broadly speaking, integrating security. Now, one of the primary things that VXLAN leverages is this notion of a overlay, i.e. a tunnel-based system that runs up on top of the underlay. And one of the things about the overlay that everybody needs to understand mechanically is this notion of something we call the VTEP. And the VTEP is the virtual tunnel endpoint, and it is really responsible for the encapsulation and decapsulation work that goes on in the fabric. So if you look at this illustration, we preserve the VLAN integrity here in terms of Ethernet is running on the southbound side of the fabric. We have the leaf switch providing the VTEP establishment, which is where encapsulation and decapsulation happens. The underlay then moves everything through the fabric, with the overlay carrying all the host-based routing and other things via something we call a VNI. And the VNI is the virtual network identifier. And there is a direct one-to-one relationship between a VLAN and a VNI. And that is how we buckle these two technologies together such that they can work in a coordinated manner. Now, if we look at the structure for how a VXLAN network almost always gets built, it's using something known as folded cloths, two-tier leaf spine technology, or what you may hear called fat tree technology. The point is, it is a two-tier model in the most prevalent sort of design scenarios. We have spines at the top end, we have leaves at the bottom, and you notice it's a completely symmetrically connected network. Leaves connect to spines, and they mesh to all of the spines. Spines connect to all the leaves. We see no lateral connectivity between the leaves, no lateral connectivity between the spines. And in the underlay, which we're looking at here, we run a L3 routed set of point-to-point interfaces so that everything is forwarding, and we have that ECMP-based underlying set of capabilities in the fabric. We give you the choice to run OSPF, ISIS, or BGP, the eBGP variant of that. And so while ACI, as an example, defaults to using ISIS in the underlay, in the case of VXLAN EVPN, we give you a choice. 2 link state protocols, 1 path vector protocol. Now, if we look at the overlay part of this, we talked about the fact that the VTEP is really the kind of workhorse function in VXLAN, where I do all the tunnel NCAP and DCAP. And what's really important to understand here is as you look at the namespace, The namespace is only relevant to the places where VTEPs are established. So what do I mean by that? That means the leaf switches are really the only devices in the fabric that understand the tunnel encapsulation. Said a different way, the spines know nothing about that. They are IP forwarders. They are intentionally only aware of the VRF. Okay, so that is intentional and done on purpose, so the spines are very lightweight, they're very lean, they're very high performance. Now, there is an exception to this rule that we'll talk about when we get to the border gateway. So the border gateway is how we establish multi-site and or cloud connectivity. And at that point, we will make the case, or we will introduce the notion of building an additional VTEP that sits at the spine layer. I think I skipped a slide there. The other thing I want to go through, and we're going to cover in just a moment here, is this idea that while our switching infrastructure at a hardware level is very versatile, you can take a modular or a fixed switch and position it anywhere in the network you want. It can run as a leaf, it can run as a spine, it can run as a border gateway or a border leaf. The more important part of that conversation is not so much the hardware, because the hardware part is kind of an easy conversation in the sense that that's generally a speeds and feeds, a port density, and a fabric capacity conversation. What we want to understand here is what is the roles and responsibilities and who's who in the fabric, and what do those capabilities bring the fabric in terms of responsibilities. So let's start with the leaf, and the leaf is arguably the place where the most work goes on, because this is where all of the devices in the fabric typically are going to connect. All the servers, the bare metal, the VMs, the containers, the firewalls, load balancers, you name it. This is also where we build all of the BGP relationships to the spine. And we also perform all of the VXLAN NCAP and DCAP at the leaf layer. We talked about that because this is where the VTEP gets established. This is also where the Anycast gateway lives and runs. I've got a slide that will describe and talk about that. And then additionally, there is also responsibility for what I will call multi-destination traffic, or how I forward broadcast, unknown unicast, and multicast traffic via something known as the BUM service. And that service can either run as multicast-based or ingress replication-based, or what we know as head-end replication. Now, if we look at the spines are different. They are lighter, they are leaner, they have no VTEP sort of activity unless they get characterized as a border. Now, the spines do a couple more important things as well. In addition to forming all the adjacencies with the leaves, they are responsible for being the route reflectors. Now, one of the things that everybody should know about EVPN is EVPN is essentially based on multi-protocol BGP, or an iBGP variant. It's multi-protocol because it can carry both unicast and multicast. And given that, many of you know, if you've run BGP, you know the way we distribute routes and we avoid full mesh is using something called the route reflectors. And so the spines will be the route reflectors, so that as a host comes online and advertises the existence of that device, the spines will radiate that to all other hosts in the fabric, such that I don't have to ARP for that at any point in the future. I will ARP one time and then everybody will learn that. The spines also are the Anycast RP for the purposes of that BUM service if you're running multicast. So they are going to be the ones that will receive the initial copy from the leaf, and they will fan it out and distribute all of that, all Fox's destination traffic to the fabric, so I can figure out how to subsequently install that into the routing tables. Now, for today's conversation, you can make a case that the border gateway might be the most important role in the network because it is the exit point for the fabric. It is also how I connect multiple fabrics together. Okay, so as we look at this functionality, if we characterize it as a border gateway, that means we are doing DCI work, data center interconnect, and we are connecting VXLAN between multiple discrete fabrics. And so you see that illustrated here where I've got a single fabric here, single fabric here. They could be at physically different sites, or they could be in one very large data center with multiple halls, or AZs, if you like the cloud nomenclature. And the border gateways are responsible for a separate discrete overlay that does all of the tunnel stitching. So I can stretch L2 and L3 services safely and very, very efficiently. It also allows me to scale beyond what a conventional single fabric is going to give me. And the other thing that's so well liked about this is, many of you know, historically we've had to run a different protocol for the data center interconnect technology, things like OTV, MPLS, VPLS. Now I have the ability to run a homogeneous protocol inside of the local fabrics and then across the respective interconnect that buckles those fabrics together. Now, as we talk about cloud, we're going to recharacterize the border as either a border leaf or a border spine, and that is for external connectivity, not between fabrics, but that will be how we attach to the cloud, how we attach to the WAN, how we attach to anything that is not known organically to one or the multiple fabrics that are connected here. Now, the other thing, for the purpose of security, because we're going to talk a fair bit about security through the course of this session, both on-prem and in the cloud, this is important to understand in the sense that this is what a classic tenant looks like inside of VXLAN. And we talked about at the outset that VXLAN is multi-tenant by nature and by construction. And as a result, you've got an ability to layer in security in an extremely effective and efficient manner. And how we typically architect a tenant is using this notion of multiple VLANs mapped to individual VNIs. We talked about that being the virtual network identifier. So it's the equivalent identifier in VXLAN to the Ethernet VLAN. We build all those respective mappings, and inside of a tenant, there can be one or multiple of those. And then we add a VRF, which is where all of the routing happens. And so, as we talked about at the outset, VXLAN is versatile in the sense that it can support bridged traffic, MAC only. It can support routed traffic, L3 type of traffic, and it supports integrated routing and bridging, so that I can do both of those across one transport. And that's one of the other reasons it's so well liked and so well suited for a lot of what goes on in the data center at a connectivity level today. Now, let's go through some terminology here, because we're going to definitely need to have an awareness of some of how the forwarding works. And if you look at the forwarding, and if you know how BGP works, then this should be very, very similar or identical looking terminology, in the sense that we are using the exact same structures, right? Where we have the VRF, and then inside of the VRF, we use what's known as a route distinguisher and a route target. The route distinguisher is nothing more than the explicit identifier of what device has sourced the routing information as it ingresses into the fabric. And then the route target is the explicit way that I import and or export routing information. So what does that mean? What that means is it allows me to selectively be able to forward traffic only to interested receivers. So if a receiver raises his hand and says, hey, I'm on the same route target, I want that information, I'm part of the same VRF, I will forward it to him. If they are uninterested and not a participant, I will not arbitrarily flood that or send that to uninterested receivers. So this is the way that I structure efficient routing across the fabric. Now, the other thing that we mentioned, and I'm going to explicitly cover Anycast Gateway and also VPC in a moment, but in addition to a lot of what we talked about at a standard forwarding level, VXLAN provides another set of services above and beyond that. So we talked about using ingress replication for the purpose of multi-destination traffic. We've also got built-in ARP suppression as part of the organic fabric behavior. So again, it is intended and built to be much more efficient and structurally the structural integrity of it is a lot more, it's a lot better than spanning tree. That's what I'm trying to say here. Now, let's look at virtual port channel. And for those of you that are also have a question about ESI, because ESI is the standards-based variant of VPC, we are going to be supporting that in the next release of NXOS. So if those of you are multi-vendor, or if you are very much of the mindset you want to be standards track, we will start supporting ESI, which is an equivalent technology here. VPC's been around for a long time. VPC still plays a very pivotal role in the fabric, because for anything that is dual attached, and the vast majority of devices in a VXLAN or a data center should be dual attached, this is going to be the technology I use southbound of the leaf to provide that dual attached connectivity. And we provide the ability to do either explicit peering, where I connect the leaves together. So here's an exception where we talked about where leaves don't connect to leaves unless we build a VPC relationship. Better yet, as of 9.23, we support fabric peering. So you no longer need to explicitly cable these partner switches together. I can build that peering relationship across the fabric and use the much more resilient architecture to provide all of that connectivity. Now, the other thing to know about this that's important, as you might imagine, because remember, VPC builds a Anycast VTEP, right? Because I have two paths and I need to announce the fact that that server is being virtualized and considered as two-path available in the network. So that is important to understand that these are individual VTEPs, but I use a common Anycast VTEP. And I do that because from the fabric's viewpoint, there are two ways to get here, but I want one address to represent that server. And then I use hashing and other techniques to ensure no duplicates and that I am forwarding down the appropriate path based on using a lot of the UDP-based entropy characteristics of VXLAN EVPN. Now, the last thing I want to cover here around the VXLAN forwarding is something known as distributed Anycast gateway. And if you think about how we've historically built the classic three-tier architecture, we laid out spanning tree, figured out where our bridge responsibilities lived, and then we added routing across the top of it. And in particular, we used something like HSRP, VRRP, GLBP to provide default gateway. Typically a base 2 system, a primary and a secondary, and we had a way to alternate priorities to go active-active. I have a much better mousetrap inside of VXLAN in the sense that now I support something called Anycast Gateway. Anycast Gateway means anybody that is a part of a VLAN can be a participating and active member being an active default gateway. So in this simple illustration, I've got 6 switches. I've got 2 VLANs that straddle all 6 of those switches. And each and every one of these can be an active default gateway forwarder. And the way this works is, based on where the host lives in the fabric, it is always going to favor the locally closest ingress switch for purposes of default gateway. The other thing we do here to make sure efficiency is maximized is we never let a switch, or a host rather, ARP for a far end default gateway across the fabric. Because technically that could happen, and that's highly, highly inefficient. And so we discourage that behavior and we actually disable that as part of how we mechanically build our VXLAN implementation. Okay, let's take a quick breath and pause. Are there any questions about what I've covered here? If there are, I'm happy to take them now. If not, we will then kind of pivot into multi-site and start talking how we enable more than one data center connectivity and how we get ourselves ready to attach to the cloud. Okay. Okay, so we talked about the fact that VXLAN is a versatile and very ideally suited technology to not only provide all of the local fabric connectivity, but what we characterize as data center interconnect or multi-site. And as part of the standard, VXLAN gives us a multi-site architecture, and it allows us to create a dedicated and explicit overlay that is responsible for all of the east-west traffic manipulation and forwarding and all of the tunnel stitching at the border devices. Now, one of the things that happens as a result of multi-site is a much more structural integrity that mirrors the fact that I built 2 data centers for a reason, and that was for isolation, redundancy, and scale. And I certainly don't want to take a data center interconnect technology and then build a extended fabric that creates one sprawled large fabric. And so the border gateway gets introduced. It is right here. You can see in this case, it is also the same device that is the spine. So in many cases, we support dual role here. And the border gateway is going to build relationships with his constituents on the other side and create an explicit overlay for the purpose of site-to-site traffic. So it carries L2 and L3 traffic, and it does all of the necessary tunnel stitching for me to extend L2 and carry L3. So this becomes a very, very pivotal device in the idea or in the sense that this is the enabler for the multi-site architecture. Now, a better example, and I noticed this morning, unfortunately, I've got an error in this slide. So on this side, it should not say border gateway. So you can kind of mentally take that out here because that was a miss on my part. But if you look at the left-hand side, in the absence of border gateway, if I just build a top-level super spine to connect 2 fabrics together, I now create what's called extended overlay relationships, where I am literally establishing a VTEP between a leaf here and one here. And as a result of that, we see all of the added replication traffic that happens because of all of the broadcast radiation and other things. So the point is we don't want extended overlays. What we want is overlays that look like this, where traffic is localized to an individual fabric. And in the event I need to get to the other side, the only device I need to know about is the border gateway. So if I don't know it locally, send it to the border gateway, and the border gateway will have relationships and be able to understand how to forward to the other site or the other multitude of sites that may be on the multi-site fabric. So it's very much like the internet default gateway. We don't advertise anything, send it to the default gateway, and he will figure out where to go. Now, the other thing that this enables for customers is a wide set of numbers of devices that we support, not number of devices, number of sites that we connect to. So we support up to 128 explicit fabrics as part of this architecture. Now, Reason may say I'm probably not likely to have 128 different fabrics, so this number is probably much beyond what most customers do or don't need. But the more important thing here to understand is this also directly speaks to scale. So if we look at this, again, in the absence of border gateways, if I just physically attach this, look at all the additional VTEP relationships that I have to create. And today in a fabric, we support 256 explicit VTEPs. And so that is a fixed number. And so multi-site, by introducing the border gateways, negates the need for me to establish VTEP relationships with leafs and other fabrics. All I do is do local VTEP reachability, and I do VTEP reachability to the border gateways, and then the border gates do the multi-site overlay. So that's how we glue all of this together in a more efficient manner. So at the end of the day, it's all about data center interconnect, as we talked about. But for the purpose of today's conversation, I'm going to go here and then I'll back up one slide. The other capability that this gives us is the ability to connect out to the public cloud. Okay, so we're going to spend a lot of time in the second half of this explaining how we enable connectivity to the primary 3 public cloud providers and how the exit point looks just like another fabric and how we actually use SD-WAN and other capabilities to opportunistically connect to and from the public cloud. Now, if I go back one slide, the other thing that Border Gateway gives us that in many cases is an extremely useful function is something called headless border gateway support. So think of it this way. I'm bringing in VXLAN technology into the environment new, and I build a small fabric, but the pre-existing brownfield environment does not go away. You know, there are truly very few to no green fields. So this allows me to take any pre-existing architecture, 3-tier, fabric path, you name it, and I can install a couple border gateways north of the core, and I can provide VXLAN connectivity and all of the data center interconnect services to the net new VXLAN fabric, and then allow a very gradual and steady migration away from this fabric and allow me to eventually sunset that and then bring this up to VXLAN on both sides. So this headless behavior or capability is very, very useful for steady and very, very conservative migrations if that's in fact how you want to go about bringing VXLAN into the environment. So this kind of gives you a summary. We've talked about all of this, Border Gateway being the pivotal piece of this architecture and going to be the piece that we talk about relative to how I connect out to cloud. Now, let's start moving towards security here. And let's talk about how we fold in security into the local fabrics. And then that'll move us to the point where we start introducing cloud connectivity. So recently, we have brought in technology that facilitates something called group policy as part of our VXLAN EVPN deployment. Now, segmentation is generally thought of in 2 ways. There's coarse grain, i.e. macro segmentation, and there is fine grain, micro segmentation. And in most customers' estimations, they typically are going to say, well, we want both of these, but they typically start here because it's a little easier to introduce and manipulate. And eventually, as they understand better what policy needs to look like, they will move to a micro segmentation sort of balanced approach. Now, one of the ways that has still been preserved inside of VXLAN is private VLANs. And this is actually quite aging and old technology, but it still proves very, very useful in some cases, and it is pertinent because we have extended this technology to support VXLAN. So if you're using private VLANs or you find this is useful, we support this as part of a VXLAN implementation. The technology hasn't changed. You've still got these explicit roles where I essentially divide downstream who can talk to who, and then this shared exit point that they can get in and out of the broader network as a whole. So this may be one technique that you leverage for the purpose of segmentation. Now, more commonly, we are seeing customers introduce macro segmentation this way, where by way of simple illustration, you remember we talked about the fact that in any structured VXLAN tenant, I have a variety of VNIs mapped to VLANs, and then I have a VRF. And so in this illustration, I've got 2 VRFs, and in this case, I've also denoted that I have firewalls here. And so this is going to provide the ability for me to provide control how forwarding happens between the blue and the green VRF. And I do that by service stitching or service redirecting the traffic to the firewall. And the firewall will make its packet manipulation and or policy decisions, and then we will ultimately send it back if that's in fact what the firewall has decided needs to happen. And we do this using enhanced PBR. So all of that logic for service redirection is enhanced PBR underneath the hood. And so for those of you that have firewall infrastructure and have security teams that are fairly regimented about how we do security up to layer 7, this is in fact how we would do this in a VXLAN-based network. Now, the GPO technology, which is fairly new, it was introduced about 9 months ago, is a technology that is now organic to VXLAN that provides me the ability to not only do the macro segmentation level security that I just described at a VRF level, but now allows me to segment east-west traffic. It allows me to reduce the attack surface, and it allows a lot of compliance-minded activities. So this is the standard that we're talking about. As I said, this is a ratified function that is now part of the broader VXLAN forwarding complex. The way this looks is very much like TrustSec. So for those of you that know TrustSec, and we've talked about TrustSec for a long period of time in many of our campus deployments, we're using the exact same mechanisms to be able to group traffic and then be able to associate explicit groups to a set of policies. Okay, so we've extended that technology and standardized it so that now this will run on top of a VXLAN EVPN fabric. And let's look at how that actually will manifest itself here. So if we look at the micro segmentation technique here, we're using this grouping logic. And think of grouping nothing more as I'm going to take half the audience here and half the audience here, and we're going to characterize them into groups. Now, we know in the data center that there's no humans typically behind devices, so these are typically servers or VMs or containers. And then as a result of this being divided in half, I can then determine how I want to enforce traffic movement between said groups. And I can either do that just by writing access control lists that are associated to that group membership, or I can add on the ability for me not only to use those access lists, but I can hook it through a service device like a firewall to provide more regimented control at those boundaries. Now, how do we do this? There's really a set of header extensions that get added to the VXLAN header, and in point of fact, there's really only 3 bits that you need to be aware of and are pertinent here. You essentially have a flag that says, hey, the group-based policy flag is turned on, right? So I'm using it. You have a flag that says, in addition to the groups themselves, I have policy following. So I've got a set of rules that are going to come in a coordinated manner. And then I also have this interesting flag that says, I don't want to learn the source address of the encapsulated frame. And that's for the purpose if you want something to not send anything back in the fabric, I can set that do not learn bit. Now, let's look how it actually works. So as I said, I am going to associate, or if you want to broadly characterize this as classify, I'm going to use a set of classifiers, and this is typically the classifiers we support today, that are going to facilitate moving devices into a respective group. So based on either IP VLAN or port in VLAN shortly, I'm going to move these devices into the groupings. And then upon moving them into the groupings, I then associate a set of policies, or what we know as SGACLs. And this is how I'm going to write all of the controls into the respective switching infrastructure that governs what connectivity, how connectivity happens. So let's look at this more specifically. I've got the example where I'm suggesting we're going to allow SG1 and SG2 to talk to one another, and I'm going to, sorry about that. I'm going to write explicit policy that governs how that connectivity works. And this is all coordinated as part of the broader VXLAN. Now, some of you may know we have supported this in ACI for some period of time. Now in ACI, we actually write this into the switch TCAM tables. So we do this in the data plane. Here it's slightly different. So we don't write it into the CAM tables. We carry all of this information in the control path, as you see illustrated here. The nice thing about that is we don't have any TCOM exhaustion problems to deal with, which has historically been an issue in very large ACI deployments. The issue here is control plane, of course, has a point when we need to move into the data plane for said scale considerations. So I think the day is going to come when we'll move to having a knob to do it in both places. But do understand we do it slightly differently than we do in the case of ACI. Now, the way this works is you effectively have two modes for how you can run the fabric now, or how you run an explicit VRF. You can run a VRF in what's called unenforced mode, or think of that as classic mode, where there is no associated policy. So as long as the underlying connectivity facilitates point A and point B talking to one another, I will freely let them communicate with one another. And then the minute I set that flag to introduce the GPO, it moves the fabric or the verb to enforced, and then I have a set of associated policies that governs connectivity. Now, the last thing that everybody needs to know here, as you might imagine, is what if I have a mixture of fabrics that do and don't support policy awareness? I have the ability to interoperate between policy aware to policy aware, policy unaware to policy aware, and then also the reverse direction. And this tells you where we are actually enforcing. And there are differences in those approaches. So it is worth understanding where I actually explicitly will build the enforcement point based on which of these models you in fact end up deploying as a customer. Now, the last thing as part of this, and then I promise we will move into the cloud conversation, is we are also in the process of building service chaining to extend that capability beyond just the L4 ACLs that we provide. So for some customers, they will tell us, well, I'm glad you have this in the fabric, but ultimately I need more rigorous security, and that is a firewall. So in addition to having this, by this time next year, we will then have the ability to also service stitch this to a firewall complex of your choosing. You know, whether that's Cisco or Checkpoint or Palo or Fortinet, you'll be able to opportunistically determine who that, vendor should or shouldn't be. Now, the one other thing I want to talk about before we get to the cloud here is a very important initiative that Cisco is working on called group policy. Or not group policy, I'm sorry, common policy. I'm tiring here. So common policy is very, very interesting in the sense that if you look at the problem statement, and we own some of the responsibility for this problem, you've had a variety of platforms that build their own individual policy models, their own individual enforcement points. And to be fair, we haven't done as good of a job of integrating those platforms as we should have. I don't think anybody would disagree with that statement. Now, for those of you that have decided to implement ICE as your prevailing NAC product, we are now building towards using ICE as the centralized kind of nerve center for where I learn and understand all of the policy information. So what do I mean by that? ICE is typically in a TrustSec model where I build all of those SGT groups and the associated IP address relationships and also the associated policy relationships. So wouldn't it be great is instead of having every platform build its own logic, I could query ICE via bus mechanism. I could understand those relationships and I could then do all the rendering myself, meaning I could write policy in one place and I could then have that naturally flow into the respective platforms. And over time, I could ultimately share that with more and more platforms. So today, we are already supporting this between our SD-WAN platform, our campus platform, and our data center platform, and our SSE platform, so that you have common ability to create group logic, the mappings and the bindings to the respective IP addresses, and then the associated sets of controls. So over time, we are going to move more and more directionally to a place where we have one place for you to build policy, because I think, as everybody will attest to, building policy is not easy. So we certainly don't want to ask you to build it more than once, and we've been guilty of that up until now, okay? So work in progress, but a very, very interesting and I think productive thing that we're trying to do to simplify your way to deploy our platforms. Okay, let's get on to cloud here. And so I think it's fair to say that, there's virtually no one that is not leveraging public cloud in some manner, okay? And how much you are or aren't doing with cloud, of course, is a company decision. But I think the thing that we believe here is cloud is nothing more than an extension of your data center platforming and technology. And what I think most customers now understand is this is a decision about where it best makes sense to run workloads. Or do I consume workloads via some sort of SaaS service? So ultimately, what we're going to spend the next chunk of the session on is how do I make the data center and the respective rented data centers, i.e. clouds, act in one uniform manner so that I can instrument network connectivity and security between them. And how I'm going to do that in most cases is through the use of SD-WAN, because I think most customers today are of the belief that SD-WAN is the modern way to programmatically build and create our WAN infrastructure. Okay, and so we're leveraging SD-WAN to not only provide connectivity to sites, because that has historically been how we have exploited and leveraged SD-WAN, but now we're also going to leverage it to interconnect a site that we happen to call a data center, and then we're going to enable all of the facilitation of connectivity, and then at a later point, security into the public cloud. So this naturally looks like an extension, and we're going to talk about how our orchestration platforms allows you to configure all of this from one central place. So for those of you that know our former Viptela SD-WAN product, we now call that Catalyst SD-WAN. I think everybody knows that. We also have a Meraki variant of this, and there's similar technology available there. But at the end of the day, our SD-WAN platform has moved into a much more broad set of services that it facilitates connectivity for. So it's not just a matter of connecting sites together, which was the original use case for SD-WAN, of course, and that still prevails today. It is now about taking these sets of rich services. So we have Cloud Interconnect, we have a Cloud Hub, we have Cloud On-Ramp, and we also have On-Ramp for SaaS that we're going to go into how these use cases work and how I coordinate all this connectivity from one platform. So at the end of the day, this is what the kind of next generation of an SD-WAN implementation in theory looks like, where I have got enterprise DCs, I've got enterprise sites, I've got public clouds, and I've got SaaS services. And I may well have a backbone that bolts together things like cloud connectivity and or colo connectivity. And we're also going to talk how the colo plays a very pivotal role in terms of interconnecting all of this and meshing this into one uniform fabric that provides that security and connectivity I talked about. So here's what this looks like at a little more granular level. So I have SD-WAN managers sitting here, and I have direct integrations into Amazon, Azure, GCP. I don't illustrate Ali Cloud, but I also have that as part of the workflow process here. And on a manual basis, we can integrate with Oracle or OCI as well. You'll also notice at the bottom this notion of the colo, and I think it's fair to say most customers are looking at a more distributed architecture that in many cases will leverage the colocation facilities. And so we're going to talk about how that also factors in as a connectivity asset that you can leverage and build into your SD-WAN capabilities for extension in and out of the public cloud infrastructure. So at a simplified level, and nothing is as easy as 4 steps, so let me be clear about that. But generally speaking, there are 4 main steps to get this on its feet. All right, and one of the things that we've done here is we have been
very conscious of the fact that just about everybody already has existing cloud accounts, cloud connectivity, and so there's no greenfield here. So we associate to all of your pre-existing cloud connectivity. We're not going to force you to go build net new. If you have infrastructure in place, and most of you probably do, we're going to associate to your cloud accounts. We're going to create the necessary gateways. We're going to build tags to associate to the respective VPCs, VNets, or whatever the vocabulary said cloud provider is using. And then we can even go so far as to map VPNs to tags. Now, the other thing is, no solution is complete without a set of requisite abilities to be able to visually understand what's happening at an operational level across clouds. And so in addition to our pre-existing capabilities to view what's going on in your privatized SD-WAN environment, we've now extended a lot of this connectivity such that you can see what's going on up in the cloud as well via the vAnalytics capabilities that we provide as part of this. If any of you actually also run Thousand Eyes, and there's probably a variety of you that do, we also have now extended Thousand Eyes connectivity to understand what even goes on further into the cloud infrastructure. So that is a complementary technology that, while we're not covering it here, can also be augmented and integrated with what you're doing with SD-WAN and also the data centers that are positioned here. Now, I want to step through some examples of how this actually looks. And we're going to go through it for all three providers, so we'll give you illustrations of how this looks. And so typically speaking, we start with a standard looking deployment of SD-WAN that is in all likelihood building WAN connectivity. And what we're going to do is we're going to establish a transit VPC or a NetOps account where I'm going to install the Cat8 KVs. And these can be either something you buy directly from us and then bring your own licenses, or you can buy them right off of the respective cloud provider's marketplace, and they can install them automatically right into the respective account that you're associating them to. So what we're going to do once those are in place, we're going to extend SD-WAN up into the public cloud. So think of this as essentially now a stubbed site on our SD-WAN network. So I've just taken my structured connectivity that was here, and I've moved it up to the edge of the cloud and cozied it up next to Amazon in this case. And I have the ability to then also integrate with Transit Gateway, right? Transit Gateway is Amazon's primary networking technology that runs in their public cloud variation. And so I will connect to the Transit Gateway, and I'm going to do that by establishing a IPsec tunnel or a GRE tunnel, could be either of the two, and I'm going to run BGP so that I can exchange routes, because I need to be able to take and advertise all of this information out to their respective places where my constituent users are. So I build all of this via API calls. And so SD-WAN Manager now not only is configuring the entire balance of the structured connectivity you own, it has also been capable and has extended all of the orchestration to build all what you see illustrated here from one central provisioning tool. And it's because we have use the publicly exposed APIs that Amazon gives us. Now, some of you may know Amazon has recently modernized and moved from Transit Gateway to Cloud WAN. Okay, this is their more modern way of building out WAN, okay? So we now also support the ability for you to integrate with Cloud WAN. So depending on which technology you're running, it can be either or. It's the same process in terms of I create that NetOps account, I'm going to build the requisite infrastructure, I'm going to associate BGP, and then I'm going to ensure that all the advertising of the respective workloads are going to be moved out into the SD-WAN network where all your devices and or users are going to exist for the purposes of attaching to those applications. Cat 8KV, as I said, is our virtualized variant of our iOS XE platform that runs on-premise, and that is the Cat 8000. That is the successor to the ASR platforms. And so this is a VM-based version of this platform. It comes in a variety of t-shirt sized deployments, think small, medium, and large, and that is respectively mapped to the requisite set of compute connectivity that needs to run in Amazon to support this. And in addition to it being t-shirt sized, it is also sized based on throughput. And throughput is steadily getting better and better and better here. We're at the point now where in a couple of the public clouds, we're able to push near 40 gig of sustained throughput across a virtualized router. Go back 2 years ago, that was at about 2.5 gig. So we've made a lot of steady progress here where now you've got very rich connectivity and you've also got extremely high performance capabilities. And we're working towards moving that to 100 gig because increasingly, believe it or not, we have more and more customers connecting at 100 gig to the public cloud. Now, I'm not going to illustrate or bring in all of the clicks here, but I do want to make sure we understand that the same technology capabilities exist for Azure. And so you see some of the vocabulary has changed. Azure uses something called the vWAN hub. So instead of transit gateway or cloud WAN, I now have the vWAN hub here. I've got the respective VNets and the peering that gets built, and I'm using SD-WAN Manager in the exact same way I did for Amazon to build connectivity across Azure. And the thing that should start being triggered in your head here is from one place, I can configure all of my on-premise and whichever cloud providers that I have relationships with. Now, you could also opportunistically, if you wish, take a tool like Terraform and use that and have that talk to our SD-WAN manager and make that part of a CI/CD pipeline or infrastructure as code if you wish. So we give you a variety of options based on how you've operationalized your network already. We also support the ability to do multiple vWAN hubs. So for those of you that may be running in Azure and have a fairly large scale deployment, you may well have gone to this diversified distributed model. And if you've in fact done that, we can integrate with a multi-hub vWAN deployment as part of our Azure integration from the SD-WAN Manager platform. Last but not least, Google. We've got the same sets of workflows using their structured cloud connectivity and provisioning. We do all of that from the SD-WAN Manager. Now, believe it or not, we also support the ability to do connectivity between the clouds. Now, this is a growingly interesting use case. Early on, I think most customers had a feeling that I'm not going to be separating workloads between public clouds. It doesn't make a lot of sense. But we have growing indications that there is communication going on between clouds because maybe I've got an S3 bucket that I dip into as part of a transaction from a workload that's running in Azure, as an example, or something like that. So as part of this, we also can facilitate provisioning where I can bolt together multiple clouds and provide cloud-to-cloud connectivity. Now, as you might be inclined to ask, this is illustrated as over the internet. And that comes with its necessary set of, hey, there's qualifications here because the internet has got some associated risk. You'd probably want to run a encryption technology of some sort. More importantly, we've got additional examples I'm going to go through that talk about how I do this on a privatized network, leveraging the colos and other things. So I'll get to that in just a moment. You can also do security stack insertion. So if you've already implemented a security set of substrates in the public cloud here, here, or here, I can then also facilitate service chaining. So remember the service chaining logic that we talked about in the on-premise fabric where I can take PBR and redirect to a set of firewalls. I have the exact same capabilities here, but I'm going to do that based on virtualized infrastructure that has been installed into the public cloud. I'm also going to talk about multi-cloud defense at the end here, which is a cloud-native firewall that we can introduce to potentially augment some of your security connectivity in the cloud. Now, for those of you that are familiar with SD-WAN and our SD-WAN platform, you may know that we support something called multi-region fabric. And believe it or not, multi-region fabric can also be configured and provisioned across the public cloud infrastructure. So if you actually want to leverage the public cloud infrastructure to take and interconnect a set of regionalized SD-WAN clouds and or facilitate connectivity to the public clouds, I can uniformly build one architecture around this multi-cloud set of capabilities. So hopefully what you glean from this is the SD-WAN platforming has evolved so that it is well beyond just connectivity to your sites and data centers. It's also facilitating orchestration to all of the public cloud providers. Now, the next thing I want to talk about, software-defined cloud interconnect. Yet another acronym for everybody to remember, and by this time next year, we'll probably have changed the name of this because we're notorious for doing that. We have established a set of relationships with Equinix and Megaport. You can expect that list to grow. Digital Realty Trust is being worked on. Some of the SPs are being worked on as well. But many of you probably have leveraged colocation-based infrastructure. And you may be asking, well, couldn't I use some of the colocation's infrastructure assets instead of the internet, as an example, to be able to opportunistically create connectivity between SD-WAN fabrics, data centers, and public clouds? And the answer is yes, I can absolutely do that. And I can also do that for cloud-to-cloud connectivity using the SD-WAN manager orchestration that we've already been talking about. So from that interface, essentially how this works is if I'm going to connect to somebody like Amazon, right? We talked about this chunk of this up until now. Now you'll notice that there's a difference here, right? So for those of you that have gone to the trouble of building non-internet-based connectivity to the public cloud providers, you may run Direct Connect to Amazon, Express Route to Microsoft, whatever. I can now facilitate using the DXG or the Direct Connect gateway, and I can build that connectivity as the underlay instead of using the internet. And I think this is probably a much more well-liked approach so that I can essentially come in through the colo and I can then cross-connect to the Direct Connect gateway, and that can then take me to the cloud. And so if you think about somebody like Equinix as an example, they run the ECX fabric, okay? And this is essentially the ECX fabric that is allowing me to cross-connect between sites, data centers, and public clouds without having to traverse the internet. So this becomes a very, very interesting way that we can think about using dedicated connectivity versus shared connectivity like the internet. Much like that, we support the same thing, and my clicker seems to be running out of gas here, but a second. Same idea with Azure, right? So instead of Direct Connect, it's Express Route. So we talked about that. You got Express Route in terms of the edge router. Same idea, just with the Microsoft variation of this. And then for Google, again, same thing. So I won't belabor the point here. I think you get the idea. Now, the other thing we talked about is cloud to cloud may be something that you, in fact, are looking to facilitate. And if you're going to, in fact, do that, in the previous example we talked about, we said this was going to be over a public transport, the internet. In this case, if you have a relationship with Megaport or with Equinix, I can privatize all of this transport so that I can go across their network, use all of the rich set of cross-connect services they have, and I can then privatize all of that connectivity between the respective public cloud providers if traffic is in fact traversing between clouds. I think I can't stand. And we support the same multi-region fabric architecture that we talked about with SD-WAN. In this case, instead of running across the public-based infrastructure, we're now using the co-location-based infrastructure, okay? Now, at the end of the day, what I guess I want to emphasize here before we move into the security component of the conversation is, hopefully what you're taking from this is we've essentially expanded our SD-WAN platforming to go well beyond just structured connectivity between sites and data centers, to integrate all of the public cloud providers. Hopefully most of them we talked about are the ones that you're ultimately trying to get connected to, and then ultimately also integrating all of the co-location providers. Equinix and Megaport today, you'll see others follow. Now, the last thing I want to talk about is security. And that's not done intentionally. That was just done based on kind of here's the layers of the cake. And so the last layer of the cake here we're going to chat about is something called multi-cloud defense. And this is also a very intriguing product. This is a product that came to Cisco a couple years ago via an acquisition of Valtix. Some of you may remember that name. This is a SaaS platform, and it is a cloud-native security platform that you're going to see in a moment is highly optimized for public cloud security sorts of use cases. So what does this actually do, and what does this look like? So as I said, this is a SaaS. So up at the top, there is a cloud that is essentially responsible for all the ongoing maintenance and care and feeding of this platform. And then in the actual premise-based locations in the public cloud providers, they have a stub that they essentially call a PaaS service, that is the security gateway that gets installed into the respective public cloud providers. And that is the piece of connectivity that is responsible for all the traffic controls in the public cloud. So we have ingress protection, you've got egress protection, you've got segmentation, you've got multi-cloud connectivity. So let's get into kind of what this does. Today, multi-cloud defense is supported across Amazon, Azure, GCP, and Oracle, respectively. Now, because they are cloud native, they have taken the liberty to pre-establish all of their workflows to come through Terraform. And as many of you know, Terraform is a very, very prevalent and popular cloud administration and orchestration tool. So if you're of the mindset you like Terraform, all of the workflow and the orchestration for this platform has already been built ahead of time, and you can opportunistically just take that off the shelf and use it. Now, apologies for a very tedious and graphically busy looking slide. But what I want everybody to understand about this is this product is also very interesting because it does not have a data plane. What do I mean by that? What I mean by that is they elected, or we in this case now, provide all of the requisite forwarding connectivity based on exclusively public cloud networking infrastructure. So we use Transit Gateway, we use the vWAN infrastructure, and we use the Google Cloud infrastructure. But all of the provisioning is done from the multi-cloud defense cockpit. So they literally configure all of this on your behalf from a centralized SaaS-based orchestration platform. So it is tremendously, tremendously simplified and easy to implement. And how this actually looks and renders itself, unfortunately, is another very busy diagram, but what I end up netting or yielding is this infrastructure that has pre-existing VPCs, and then you'll notice here I've got this security VPC and I've installed these security gateways. And the same thing holds true in all of these examples. And now we're going to go into how these actually work. But that is what the orchestrator has done. It has built all of the plumbing to support this, and then it has installed that cloud-native gateway into the respective VNets or VPCs. Now, one comment here to make, and I put Cisco in the same category. Many of you as a customer may say, well, I already have a firewall vendor. I've already installed said firewall into the public cloud. And that's a lift and shift activity. Ours is the same. So if you have FTD and you installed it up into the public cloud, that was just a lift and shift. And so there is some inherent inefficiency because those platforms, ours included, are not cloud native. This is a cloud native microservices platform. It is very, very lightweight. It is very economical in terms of the amount of cloud assets it actually consumes. And it is very lean at a forwarding and performance level. So it's arguably far more efficient than any equivalent firewall on the market, including ours, by the way, as it pertains to cloud-based security. Now, this product has three primary functions. It has ingress gateway capabilities, and you get these sets of services as part of the ingress gateway capabilities. So it's a very rich set of ingress capabilities. Same thing for egress. And then we also have a set of east-west segmentation controls. And broadly speaking, these both run under what they call a egress gateway, and the left-hand side is delivered via an ingress gateway. Now, multi-cloud defense has two deployment methodologies that you can select from. So the first option is creation of a dedicated security VPC. Okay, so we have pre-existing VPCs here, and we've created a essentially bump in the wire VPC for which I now install the multi-cloud gateways. You see those right here, ingress and egress. All the traffic traverses this on the way to the ultimate destination VPC. They also support an ability to distribute their gateways. So instead of hooking it through that dedicated security VPC, I can move the gateways out into each of the individual VPCs where the workloads themselves live. So if you look at this side by side, again, a centralized model, a distributed model. Now, not to further complicate matters, but believe it or not, they support a blended model. So if you say, listen, I want 2 tiers of screening, I want the ability to literally screen at a dedicated bump in the wire, and I also want to screen closer to the individual respective VPCs, I can do both. And they coordinate all that from the central orchestrator. So let's go through some of the use cases and how this actually looks at an enforcement level, okay? So we talked about the fact that this is largely divided into 3 sets of technology: ingress, egress, segmentation. So if we first look at egress filtering, okay, and we illustrate both models. And egress filtering, let's think about this meaning I've got infrastructure that has public-facing internet addresses. And as a consequence of that, there's typically a net requirement to be able to provide some sort of security before I go back out to the internet. And so in both models, they will either A, bump the wire with that security PAS device, and this is where I will do all of the enforcement before it moves out to the internet. In the case of the distributed model, it's the same idea, but the gateway is just closer to the workload. And this is going to do all of the filtering out towards the internet for anything that is got a public-facing IP address. Now, if you look at ingress, as you might imagine, this is obviously the reverse traffic flow. So now I have user here, coming here, and I'm going to either bump the wire or I'm going to hook it through the respective VPC to provide all of the requisite screening and or security capabilities before said user is granted access to whatever application is running in the respective VPCs and or VNets. Segmentation. We talked a lot about that in the VXLAN parlance in the early part of the presentation. This also provides the ability for me to govern connectivity between the VPCs themselves using the same device. And so I can either do that in the bump in the wire centralized model, or I can do this in the distributed model. So hopefully you're starting to get a sense of how versatile the product in fact is. In addition to that, they provide URL and domain filtering, and it can be done in both models. So you see the illustrations here, if that's a capability you need in the public cloud, and in many cases for public-facing public IP address deployments, that is, in fact, is going to be a requirement. Now, last but not least, much like the SD-WAN platform, and keep in mind they are just on the cloud side of things, they can provide security bump-in-the-wire services for cloud-to-cloud connectivity as well, because they've got respective gateways installed either in a centralized or a distributed design variation in a multitude of those public clouds. So it wouldn't be complete if we didn't at least show some sort of view of what the cockpit itself looks like. So this is what the multi-cloud defense cockpit looks like. Some of you may know that by way of long-term plans, this is ultimately going to get integrated into Secure Cloud Connect, which I think you probably have heard through the course of the week is our aggregate security orchestration platform. So you'll ultimately see this become a substrate under that broader security umbrella as time goes along. The other thing that is happening in parallel with that is, if you remember the common policy initiative I talked about, where ICE becomes the central place where I query for requisite tag and or policy information, the plan of record is for this platform to do the same, so that it will become tag aware, so that again, I don't have to necessarily go and build a net new tagging and or enforcement infrastructure, but I can leverage what's already there. So that's not done today, but that is something we clearly are moving towards. Dashboard-wise, this is what it looks like. Super, super easy platform to use. First time I saw it, I was very, very convinced that this was going to be more difficult, to be honest with you. But despite some of the sophistication you've seen in terms of the back end of this, it is literally a handful of clicks to get this configured, you know? And so it's really intended to be a user-friendly interface and or system. And that's why they elected to build this as a SaaS with a distributed set of PaaS enforcement points. So in closing, around multi-cloud defense, we talked about the fact that it is a platform that leverages your pre-existing cloud accounts, and it leverages cloud-based infrastructure, and we'll do all the requisite provisioning for the networking to provide that necessary data plane around the security structures they give you. Traffic visibility capabilities, ingress, egress, segmentation, okay? And it is a cloud-native, very, very lightweight, very, very, very lean platform. Okay, deep breath. Last slide we're going to cover here, okay? So we've spent a lot of time and traversed a lot of topics. What I think the final closing thought I want to give to you here is, today the way we think about data centers and the WAN and cloud is in a much more homogeneous sort of way. And so the platforming that hopefully we've taken you through and described today, respectively, is trying to unify connectivity across these various sets of assets you have. And just so you know, at a visual level, that is intended to represent VXLAN on-premise in the data center. This is the SD-WAN platform. These are the respective logos, of course, of the vendors we've talked about. The nice thing here is we talked about the fact that we've essentially got two places where we can provision all of this infrastructure. from the data center and from SD-WAN, and I can provide connectivity services that not only provide all the requisite networking, but embed very, very strong and integrated security controls as part of the broader architecture in total. I lied. I said the first time it was the last time you were going to see this slide, so it is one more time. So just by way of reminder, we do have a room. I'll be monitoring it for questions, so bear with me. I traveled today, so if there's questions, it's probably going to be next week, but you're happy to post in there opportunistic as you see fit. Slides are in this room, or they should be available on your app. I would implore you to fill out surveys. I know this is asked of you every single session. It is important. I actually am one of the members of the SGM team, so I do all of our track selection for the data center in Europe and the US. And I say that only because we want to know if sessions were good, if speakers were good, please tell us. If sessions were needs improvement, or it's a topic that we maybe need to consider putting something else in for, we need to know that, right? So if you take a few minutes and complete your survey, that'd be greatly appreciated. I think we'll even give you a t-shirt. I haven't seen it, so it may well be not even available anymore. And with that, I think we're probably at a point where most of this is either closed or there's only a few hours left, and you may have already spent enough time that you don't need to do any of that anymore. What I do want to close with is, I think a lot of you are probably traveling today, so safe travels getting home. If you have questions, I'm happy to take them quickly, although I'm one of these people that does need to get to the airport at some stage here. And I also want to thank everybody, because you may or may not know, but this week's attendance at Cisco Live in Europe was 18,500. This is a record by a mile. Historically, we've been, 13 to 14,000-ish. So attendance has been incredible this week, and that's because of you. So hopefully what we've done here has been aligned to your goals and objectives. And with that, we will draw to a close. We've got about 8 or 9 minutes, so we finished a little early, which probably on a Friday isn't a bad thing, in all honesty. So thanks again. Hopefully we'll see you back here in Amsterdam again next year. Okay.